Hello everybody. So we're gonna start with this example as the first gas-liquid separation example by distillation. And we briefly discussed this example in the previous video, and we mentioned that we want to separate a mixture of ethyl benzene, styrene, and heptadecane. We know the feed conditions, the flow rate, we know the temperature, the pressure, and the compositions here. And it's desired or required to do distillation so that we can do separation, as we will mention here shortly. And we need to know the distillate flow rate, the reflux ratio, the number of stages, so you get the basic information or the basic design considerations that we need to achieve a recovery of 99.2% of the ethyl benzene and styrene recovery of 2.5%. And we know that the reflux rate or reflux ratio is 6, and we know that the pressure at the top is 45 torrs and in the bottom is 105 torrs, and we are going to use the total condenser. So from the information we have here, there are kind of different things we can know. So the first thing, it's clear that I want to separate ethyl benzene from styrene. So it is the we can tell which of them is the heavy key and which of the light key, and this is something we discussed in the previous video. So this is something important. So it's we know the key components are ethyl benzene and styrene. We might get confused and don't know which of them is the heavy and which one is the light key, but we can tell from what's said here that ethyl benzene is desired to be recovered. Most of the ethyl benzene is desired to be recovered by the column top, and the styrene only 2.5% is recovered by the column top. So it means that the ethyl benzene is the more volatile component. This is something that we will confirm in Aspen Plus, but it's from this we can tell that ethyl benzene is the light key because it's going to be very rich in the top product, and styrene is the heavy key. So now let's go to Aspen Plus and see what we have here. So the first thing that we have is I have already defined all the components: the ethyl benzene, styrene, and heptadecane. And when we go to the or there is one other thing that's important. In some cases, like this, we have the component name and we don't know its molecular structure, so we cannot tell if it is polar or non-polar, so we can consider this as a chemical system or hydrocarbon system or the type of components we have. So one thing you can see here in the component section is the molecular structure. So if, for instance, you want to go for ethyl benzene, there is this tab of structure. It's gonna take a bit of time, but it's gonna tell you how the molecular structure looks like. So it's a benzene ring that has an ethyl group, and it's clear from the name it's ethyl benzene. The same for so there are no polar groups here. I don't have any oxygen or any polar groups here. The same for styrene. You can do the structure. You can see that it is a benzene ring with a vinyl group, which is an ethyl group with a double bond. So it's also nonpolar, and for N-heptadecane it's the same. It's a nonpolar component. It's a very long chain of 17 carbon atoms. So there are no polar components here. So from this I can tell that I'm working with hydrocarbon system. I don't have any components that can be considered chemical components that, I mean, by the definition of Aspen Plus, that will cause any hydrogen bonds or make any thing like that. So for the method, I'm gonna use the SRK. You can use Peng-Robinson, Lee Kessler, or whatever the method that the cubic equations of state that you wish. Before we go to simulation, again back to the point, which is the heavy key and which is the light key, there is one way that's very easy when you go to the specifications. We mentioned that before in a previous video, that you can find some basic basic information about the chemical components that you have. So you have here, one of them is the boiling point, and it's clear that I'm looking at the ethyl benzene and styrene. Ethyl benzene is more volatile, its boiling point is less than styrene. And N17 is way far from them, so it's not gonna be a problem. So the two components that I'm working with, the first is the light key is gonna be ethyl benzene, and the heavy key is a styrene monomer. So it's important to keep this in mind. Again, I mentioned this in the previous video because it's a very common mistake. But you have to make sure that you define the light key as a light key and heavy key as a heavy key. One other thing that we can do to know this is going to the simulation environment, or we can do this here, but let's do it in the simulation environment. I have already defined the feed stream, the temperature, the pressure, the flow rate, and the compositions. And there is one thing that you can do is to go for, or let's go from here. It's going to be easier. Let's go for stream analysis. It's not allowing because I haven't done that. So there is the file has to be run before going for this. So there is one thing I'm gonna do anyway. So I'm gonna go for manipulators, go for duplicator, and I'm gonna do this because I'm gonna use the same stream for more than one unit. So I'm gonna duplicate it, and we did this before in reactors and in many other things. So here I'm gonna go for F4 shortcut, short not sort, and this is I'm gonna keep it like this. So if I run the file, it should be, I think I forgot something because it's not happy. Okay, so there is something here. It's SRK, so I don't see any problem. So I can run the file, and it's not going to generate any new information because it's already a duplicator, so it's not going to make anything new. But I can now right click on this stream and go for stream properties. No, I'm sorry, I'm gonna go for you can go for the bubble point and dew point, but I'm interested in the stream properties, because there is one other parameter that is very indicative about the difference in the boiling points or the volatility of the components, which is the K values. So I can create a new property set, and we mentioned the property sets before, and in this property set you can search for the K values. And we need to check the vapor liquid. It's not vapor liquid 2 because it's gonna be for 2 liquid phases, so I'm not interested in this now. So I'm gonna do this for any range of temperature. I'm fine with that, and this is the pressure I'm working in, so I'm okay. And by running the analysis, we can see that I have a plot of the K values versus the temperature. It seems from the first look that the K value of the ethyl benzene and styrene are very close together, but if you take a look at the y-axis, you'd see that the scale is different. So we need to make the y-axis single. So the first thing that you notice is that the K value of the heptadecane is very low, and it's very expected, because the K value is the y over x, the mole fraction in the vapor phase divided by the the mole fraction in the liquid phase. So it's very low volatility component, so the vapor phase mole fraction is going to be very low. here is the point, that I see that the K values of the ethyl benzene is higher than the K values of styrene, which means that ethyl benzene is more volatile. So there are kind of different methods that you can follow to confirm which of them is the heavy and light key. I'm spending time to confirm this because it's gonna be a problem if you do not choose them right. And I'm gonna do this at the end of the video to do this mistake and see how the output will look like. So I'm gonna these are the units that we mentioned before. I'm gonna go for the when Underwood Gilliland method column for or the shortcut method for distillation. So I'm gonna call it short. By short I mean the shortcut method, and you have to connect the short top and short bottom, and let's see what information we have. So here are all the inputs that I need to define. They're not a lot of information. I'm gonna put them side by side so you can see which information will go which. So I don't know the number of stages. You can either choose the number of stages or the reflux ratio. He mentions in the problem statement that the reflux ratio of 6. If I don't know or I don't have an estimate of the reflux ratio, I can put any number, like put 1, put 7, and by doing this we can know later what is the value that I should change, I should choose, and this is something we will see again. For the light key, we mentioned that it is the ethyl benzene, and for the heavy key, it is styrene. Keep in mind that you are defining the recoveries, and luckily the information that we have in the problem statement are the recoveries. So we have the information exactly the same way it is required here in the software. If you do not, you have to do your calculations to know how much recovery you want to achieve. So I have 99.2% and 2.5%. So by just putting the mouse here, the information or just the hint, it's the recovery of light key component in the distillate. And the number has to be from 0 to 1, so it's a fraction from 0 to 1, or a decimal number. So it's going to be 0.992. If you put 99.2, it's going to generate a mistake. It's going to tell you it should be from 0 to 1, so I have to make sure that it is in this format. And this is kind of confusing. It says the styrene monomer, and this is the recovery of heavy key component in the distillate. So it's not what will jump in your mind that this is the heavy key or the light key. It's in the distillate, and the light key it's in the bottom product. I mean the heavy key and the light product. No, both are in the top product. So it's 0.025. And by the way, 2.5% is 0.025, it's not 0.25. It's a very, very common mistake. So please make sure that you do not do this mistake. For the condenser, it's a total condenser. You have options of going for a partial condenser with all vapor distillate. So the condenser condenses part of the stream or the top product, and it's coming back, the condensed part is coming back or refluxed, and the top product is the vapor. And that's why the distillate vapor fraction is 1, because it's totally vapor. Or you can have the option to have vapor and liquid distillate. So the liquid, some of the condensed liquid is refluxed to the distillation column, and the other part of the liquid and vapor are coming as distillate. And that's why you can choose how much vapor fraction that you need in the top product. So we're gonna go for a total condenser. And for the pressures, I know here that the pressure at the top is 45 torr. The torr is kind of like the millimeter mercury. There are very, very small difference between them, but it's almost the same. And the bottom product is 105 torrs. So I have now all the information that I need to define the column. So I can run the simulation and see what kind of output that we have. So the basic results, it says the minimum reflux ratio is 4, and this is a very, very nice information, because in case I mentioned before, if I don't know this 6 that I'm gonna use, I can put any number and it's gonna give me the same minimum reflux ratio. It's not a function of the reflux ratio that I defined. So you can put any number and it's gonna give you the minimum reflux ratio from which I can change the value of the reflux ratio. So the reflux ratio, the minimum reflux ratio of 4 means that I'm gonna use 1.2% of it, which is 5. So I can go for 5, reflux ratio of 5. And I have here the minimum reflux number of stages, which is the number of stages I'm gonna use in case of total reflux. I don't have any top product. I'm recovering or returning back all the top product to the column. So this is the minimum number of stages. It's a theoretical thing, so I know that this is the minimum number. I cannot go for less than that. And for the number of actual stages, I have 40.8, because of course this is the ideal number of stages. I didn't define any efficiencies. I know the feed stages is this, the number of actual stages above the feed is this, and the duties of the reboiler and the condenser, the distillate temperature, the bottom temperature, the distillate. This is important. The distillate to feed fraction is an important piece of information. It tells me how much of the feed is going to the top product and how much is going to the bottom, which is going to be the balance of this. And this is important because it's one information that I have to define in the rigorous mode. This is important. I have to define this piece of information. So this and this are very important, the number of stages, whoever you want to define, because and again, as I mentioned, I'm not sure if I mentioned this in the previous video, that in the distillation, I have to go for the shortcut method first before going to the rigorous method. This information cannot be predicted easily, and it's gonna be like shooting in the dark if you're going for the rigorous mode directly. You have to have some information from the shortcut mode before going to the rigorous mode. And for the stream results, we can find the mole flows, or let's go for the mass flows because we're working with mass flows or mass fractions. I have, these are the feed components. You can see that for the bottom, almost all, it's not almost, it's actually all the NC17 is recovered in the bottom product. None of them is in the top product. The styrene monomer, if you do the calculations of 285, let's try it and see how much recovery we achieved of the styrene monomer. So it's 285.313 divided by 114, 12.5. So it's 0.025. It's exactly 0.025. And if we do the same for the, so I divided this by this, and now I'm gonna divide this by this, because our recoveries were calculated based on the top product. So 15,939.7 divided by 16,068.3. So it's 99.19996. So it's 99.2. So it's exactly doing what we were looking for. So the separation is totally fine. And we know the information that we can use in the rigorous mode to do the calculations. There is one thing that we can do, which is this in the options. It's a very, very nice option. That you can generate a table of reflux ratio versus the number of theoretical stages, which means that I will ask the software to do the calculations for many reflux ratios and calculate the number of theoretical stages for each one of these reflux ratios. So the initial number of stages, the table, the initial number of stages and the final number of stages. So I'll ask the software to go for how much stages to how much stages. So I know that the minimum number of stages was 25, so I'm gonna do 26, and I'm gonna go for 60, for instance. And the number of values in the table to be 17. I'm fine with that. And this is the significant digits. It's how many decimal places or digits will be displayed in the table of the results. This is great. The HETP is the height equivalent to transfer unit, which is equivalent to stage in case of packed column. So for packed column, it's a packing, continuous packing. You don't have stages like what we have in the tray columns. So in this case, we need to define what's called a display, an equivalent, I mean the transfer unit, which is equivalent to the tray. So this is where we have, or where we can define the number of stages equivalent to the number of stages, I mean. So we cannot do this here because we are not using a packed column. And now we will do the run and see the output. Of course, it's going to take more time because we have a lot of calculations here. And in the results, you can see this tab was not active before. And you can see that this is the reflux ratio, and you can see for 26 I have a huge reflux ratio. This must be seen. We have to take a look at this. Of course, we know that as the reflux ratio increases, the number of stages decreases. So this is what we see, that for this we are very close to the minimum reflux ratio, so we had to use a huge number of stages. But for this part, when we are going for or further away from the minimum reflux ratio, the number of stages decrease. It's not easy to see from here because of this big number. So we can make the y-axis for 25. The limit of the y-axis to 25 stages. So from here you see that I can, I mean the reflux ratio. The reflux ratio was 20 when I used 28 stages, and the reflux ratio was almost 4.5 when I used 60 stages, and it's gonna go smaller as the reflux ratio increases. So this is a very, very nice demonstration to the effect of the reflux ratio on the column. So it's the rule of thumb that is that as you increase the number or the reflux ratio, the number of stages decrease and the diameter of the column increases because you are increasing the flow rate inside the column. And the other way, if you decrease the reflux ratio, you need more stages and the diameter will get smaller because you are using a smaller flow rate. So this is what I was talking about. This is the plot, and this plot is, you can imagine how much time you would take to generate a plot like this if you are doing the McCabe-Thiele diagram. You have to do, I don't know how many points I have here. There are a lot of points. I have it's not that less than 15 or 20 points, and for all these points I have reflux ratios and number of stages for each one of them by click of a mouse. So this is awesome. So anyway, so I have now all the information that I want to know so that I can go for the rigorous mode. One last thing is the flipping of the key components. This is the mistake. So I have here it's gonna, if I go for ethyl benzene, so the light key component cannot be at the same. Yeah, I'm gonna override, and this is, so it's a mistake here. He doesn't understand how the heavy and light keys are the same. So when we do the run, it's gonna display an error. And again, the errors in Aspen Plus are not very straightforward and you cannot tell. But it says that the calculated minimum number of stages is less than 0. So the minimum number of stages is negative, because it's like you're flipping the column upside down. So he cannot understand that. And all the stages are negative stages. So all these numbers are not mentioning or telling you that the key components are flipped, but from your experience with the software, you can tell that there is something wrong with the choice of the key components. So if I return back the ethyl benzene and styrene as key components, will not get any errors, and the outputs will be as we saw before. We have the plots and we have everything. So this is again an important thing. From my experience with the students, they always do this mistake and they get stuck at this point. And this is a very preliminary stage. Like you are just defining the column. It's not a problem with the output. It's just a problem with the inputs. So you have to know how to troubleshoot this problem. So this is all for this video, and I'll see you in the next video, inshallah. Goodbye.